So welcome to the pre-recording of lecture 20 of Introduction to Symbolic Computation in summer of 2022. This lecture is on recursive functions and memoization. So memoization is a technique to run programs more efficiently. So we will illustrate this on the example of the Fibonacci numbers. So this is a technique which is very useful, especially if you have a recursion that is generating an exponential number of calls. Okay, so let's look at a very simple example of a recursive function. So we are looking at the definition of the Fibonacci numbers. So the first Fibonacci number is 0, the second one is 1, and then the next Fibonacci numbers are computed as the sum of the two previous ones. So we have a simple recursion, and this recursion can be codified in Python in a nested if-else statement. So as in any recursion, we have a base case. So here we have two base cases. If the argument n is 0 or 1, so these are the two base cases, we return 0 corresponding to this definition here. We return 1 corresponding to the second base case. And then we have the general recursion. So this is a recursion that will terminate because as we subtract from the arguments, we will land in one of these base cases. You can verify this with n equals 2. For n equals 2, you call f for n minus 1. So this is the second base case. For n equals 2, n minus 2 is 0, so the first base case. So this is a function that will terminate, and it is a literal translation from the actual definition of the Fibonacci numbers. Very good and well, but the function actually doesn't work. So it is a correct function, but it will only give good results for small numbers. So in computer algebra and symbolic computation, we can work with very, very large numbers, but we will experience, and we will do this also in SageMath in the second part of this presentation, we will see that this is a very simple function that generates an exponential amount of work. One can see this already for n equals 4. So if you compute the fourth or the Fibonacci number for n equals 4, then you're not in the base case, so you compute f equals 3, f equals 2. With f equals 2, you get quickly in the base case, but with f equals 3, you have to continue. And what you observe is that the f2 is computed here, but is computed here again. Now, so what? Well, notice that the number of function calls that you have to compute here to compute f of 4 is 8. So you can count. So this is the number of function calls to compute the nth Fibonacci number. So for 2 we have 2 function calls, for 3 we have 4, so here you see the case equals 3, and then for 4 we have this number of function calls. So looking at these base cases, examining the cost of this recursive function, we can see the pattern. So 4, we have 2 to the power 4 minus 1. For 3, we have 2 to the power 3 minus 1. So this leads then to a recursion relation. So we have 2 to the power n minus 2 here, 2 to the power n minus 3 here. Plus 2 if we start to expand everything. So this is of the order an exponential number with base 2, 2 to the power n. And that grows extremely fast. So the entire problem looks like a very simple problem, and it is actually a simple problem. But if you are using the simple recursive definition that was here on this previous slide, then it is a horrible way to compute the Fibonacci numbers. So one might say that be careful with recursion, and that's certainly something that I would also support this statement. On the other hand, it's not true that you should avoid recursion. So recursion is still an extremely powerful problem-solving technique, and we will see how we can fix this problem of the exponential number of function calls with some relatively minor modifications to the original definition of the function. So what is the idea? So if we are looking at the list of the first 10 Fibonacci numbers, then we can see that if we are running, if we are computing the 11th number, we can look at the list first. So with the 11th number, we're not in the base case, and we have not yet computed the 11th number, but we have computed the 10th and the 9th. So then we can just simply, instead of calling the recursive function again, we can simply look it up. So memoization is a technique that stores the results of the function calls, and that will dramatically increase the performance of this recursive function. So to memoize recursive function, you have to decide on your data structure that you will use. One can use a list. That list will store all the previous calls. So before you have to compute anything, you check whether the number in the list or in the data structure exists. If it does not exist, if you have to compute something, you will store the newly computed number first. So here with Fibonacci numbers, a list is a natural data structure. In general, it might be better to use a lookup table, a dictionary. So dictionaries are optimized data structures for efficient lookup. So the cost to look up can then be logarithmic in the size of the data structure if it's organized well. Okay, so let me explain how now to fix our original recursion. So for, I gave it another name, but instead, except for that name, you recognize the original definition of the Fibonacci numbers that is still embedded in this definition. There are two steps that one needs to do. The first step is the dictionary lookup, and that is done here. So you check whether for a new argument it belongs to the dictionary. Then you simply return it if it's already computed. If not, you will compute it, calling the memoized versions. And before you return, you will store the result in the dictionary. Now, why does this work? So in an earlier lecture, we explained the referencing with composite data structures. So the argument of the memoized function here is a dictionary. It's initialized to the empty dictionary. So the first time that this function is called, memory will be allocated for to hold this composite data structure, the dictionary. So notice that if you declare, if you have this equality here, if you have this assignment in the definition of a function, it's an optional argument. So whenever we call the memoized function, like here in the recursion, we do not specify the dictionary. We could do that. So if you want to change the definition of the Fibonacci numbers and provide your own lookup table, then this can be done. But that's not the purpose here. So what is done, the reason why this works is that dictionaries are composite data structures, and what this function stores is a reference. It's just another name for that dictionary. So there's one single dictionary in main memory that gets updated. So each time when one stores a result here, we take the name, and the name refers to the actual dictionary, and we update it. So this function keeps on using the same name, and therefore it refers to the same dictionary in main memory. So the reason why this works is by using the terminology or using the concepts of composite data structures. We explained that in an earlier lecture. The main point, however, is that this memoization technique can be applied in a very structured manner. So there are two things that you need to change, and there is no additional proof of correctness needed because you use the original logic of the recursion. So we still have now the best of both worlds. We have the simple definition of the Fibonacci numbers embedded in our function definition, but we have two extra statements, the lookup and the storing, that make it much more efficient. Okay, so I hope to demonstrate this now in a Jupyter notebook with a SageMath kernel. So I will swap in the Jupyter notebook that I have prepared, but for the reasons to make this lecture a little bit step by step, I will make a new Jupyter notebook, and as you follow this lecture you can go along and see what it is that we are doing. So in this lecture, already lecture 20 of the 8-week summer of Introduction to Symbolic Computation, we make recursive functions more efficient, or dramatically more efficient, by memoization. So this is the Jupyter notebook that I will be using in this recording. The prepared Jupyter notebook goes onto the course website. So let's start out by defining recursive functions, and let's look at the Fibonacci numbers. So the Fibonacci numbers are defined by the following three rules. So the first rule is that the first Fibonacci number is 0. We start counting from 0. The second one is 1. And the nth Fibonacci number is the sum of the two previous ones. And this is for n larger than 1. So these three rules should be read one after the other. So you first see, depending on your argument, whether any specific rule applies. Okay, so let's define a Python function. So a Python function is good practice to have a documentation string. So there's one argument, n, and what is returned is the nth Fibonacci number. So a more explicit documentation string would also store the definition. Alright, we have a nested if-else. So the first base case is when n is null. So then we do the else if instruction, or it is the elif instruction. We return 1. And else, so don't forget the colons, I sometimes do this. So we, in the general case, we sum up the two previous Fibonacci numbers, defined recursively. So if this is syntactically correct, and it apparently is, SageMath does not complain. So let me look at the first 10 Fibonacci numbers. So we see the two base cases, 0 and 1. So then the third Fibonacci number is 0 plus 1. Then we have 2, 3, etc. And you see you can very easily verify this. Okay, problem solved. If you are unfamiliar with recursion, then you see the very nice way of computing. But I'm telling you that this does not work, and let's except for only small numbers. So let's look at the timing results. So I will start at 21. Then you see for 21 it actually went fine. So let's do 22. Well, 22, I have to wait 22 milliseconds. So let me do 23. And I predict here that I have to wait, see more than 30 milliseconds. So I can continue with this, but I hope it becomes clear that for every next Fibonacci number, I have to wait longer and longer. And this is a fast computer, but I'm very careful not to do this for very large numbers. So you see that it takes almost now twice as much. So let me see when it doubles. And here you see, well, it doesn't really double yet, but it already gets into the range where it's going to start taking seconds. So what is the problem? The problem is the exponential number of function calls. So let me illustrate this. So we have worked with labeled binary trees. So in another way, this is a very nice working with data structures, and you can kind of also see the power of recursion. So I will define the first tree of function calls using a labeled binary tree. So I have my two base cases, and my first tree is called L2. So that's the first non-trivial case. So let me continue with defining the trees for the other function calls. So I compute so let me be systematic. So I'm computing the third Fibonacci number by calling the previous two. Let me do L4 as well. What I'm essentially doing is that I am running the recursion as well, now with a data structure. And you see, making this very large tree, so I can go one step farther here, goes actually very fast. So I only need one extra instruction, and I make each time a much larger tree. So just like it is with the, so this also illustrates the power of recursion. You can also use this to fill up your memory rather quickly. So I can make a very large tree very quickly. And you see the repetition of the trees. So now the F2 occurs 1, 2, 3 times. And if I'm going to continue this, then I'm going to have the computation of F6 that's going to require F5 and F4. So each time I have this entire tree that gets added to this. So it very quickly fills up. So that is the problem. How do we fix this? Well, let me illustrate the technique of memoization with a Python function. So what is memoization again? So memoization is a technique to store the function calls to make programs run more efficiently. If you take an algorithms course, then you will certainly encounter dynamic programming, so it's very similar here. It looks as if you are replacing computation with data structures. So one has, of course, to be very careful that if what you are going to compute requires an exponential amount of memory, then memoization will not work. But as with the Fibonacci numbers, we can work with a very simple list of numbers. So the sequence of Fibonacci numbers remains bounded in the size of the number. So that is also key why this is working here. What I will do is I will make a memoized version, and to make the point that I can just keep the original structure, I will copy and paste the original function. So call this memoized, or just if you want to save typing, you just put an M in front of it. And we apply memoization for the nth Fibonacci number. So we have an extra base case. If the n is in the dictionary, then we will do the dictionary lookup. Otherwise, we have the original code. Now, of course, here is where a problem is. Why not just call f? Aha, so this is where you cannot do this. So there is a mistake that you can make here. You have to change the name of the function also in the general calls. Otherwise, there is no benefit. So we have a new function that will, and also you must store. So we have the result that is assigned. So I cannot return, I must assign to a variable result. So we store the new number before return the result. Okay, so demonstrating this in this manner, you can copy and paste, but note that most importantly, you must change the name of the function call, and you must store the result in a new variable. So you cannot return immediately. When you compute a new number, that number must be stored in the dictionary. Okay, so let me run this to have SageMath verify that this is indeed syntactically correct. And for correctness, let me compute the first 10 Fibonacci numbers to see whether I can still verify that I see the same number. And let me now time it. So now I'm feeling very secure. So I'm going to time 100, and you see that the magnitude is nanoseconds. It's really immediate. So if I will type now MF100, in some sense nothing is computed. There is just a dictionary lookup. And one sees it's a huge number, but that is no problem in symbolic computation. I can even go farther. So if you want to see the 1000 Fibonacci number, and it's not a spelling mistake, then you see the answer is immediate. Because the data structure, the cost of the data structure is proportional. So while the number of function calls into the f was exponential, the amount of storage to make the computation more efficiently is linear in n. So again, there are a lot of computations that may require an exponential amount of storage, and often that doesn't help here. So the trick what makes this work is that to make it more efficiently, the amount of storage is only linear in the dimension. It's not exponential. At the technical level, perhaps I can probably still explain this. Should say this, that this dictionary here is initialized once, only once, when this function is called for the first time. So in a way, the time will also differ. So to reset, so in order to clear everything, you will need to reset, apply the reset statement before you run it again. So the dictionary is a composite data structure, and in composite data structures we have names that refer to the actual data. So in more low-level terminology, we have an address that is kept to the single location in memory that is the start of this data structure. Each time when we store a new result, we are changing the same data structure. So that is referred by the same address that is remembered by this function. Okay, so let me now consider memoization in SageMath. So we are not limited to numbers. So we can store expressions. So in symbolic computation, we compute with symbols and expressions. So we can use the memoization to speed up recursive definitions of orthogonal polynomials. So let me take the example of the Chebyshev polynomials. So in numerical analysis, the follow-up course, we will use Chebyshev polynomials, and in general in numerical analysis, to make our computations be more accurate, we work always with orthogonality. So a very useful class of orthogonal polynomials are the Chebyshev polynomials. Defined by the following three rules. So similar to the Fibonacci numbers, we have three terms recursion. So now there are two arguments. So the first argument is the degree, and the second argument is the symbol. So the constant Chebyshev polynomial is just 1. The Chebyshev polynomial of degree 1 is just x, and then the general Chebyshev polynomial is 2 times x times the previous one minus the one before that, and that is again for n equals 1. Okay, I hope I have this right. I cited this from my memory. So the Chebyshev polynomials are already available in Sage. So that's the Chebyshev t, and here I will use x as well, and let me look at the first 10 Chebyshev formulas, Chebyshev polynomials. Okay, so Chebyshev is most likely misspelled. So now I do have to consult my preparation. So it's Chebyshev with an underscore. And without a capital C. Here we are. So what did I say what the recursion is? 2 times x times the previous one. So the previous one is x, so I have 2 times x squared minus 1. So then I have 2 times the previous one. So here you see the 2 times, each time the degree goes up, and I have always my one that gets kind of added, or I have the x. So what's the point? Well, the point again is that if I would define this in a straightforward manner, then it would be too expensive, except for the first 10 Chebyshev polynomials, perhaps. So let me now define immediately a much more efficient definition than the plain recursive one using memoization. So, and we have the Chebyshev underscore t to verify. So we will define our own definition of the Chebyshev polynomials using the rules but with memoization. So that's actually the whole point. Now, the point is also with Python, you would not, pure Python, you would not work with mathematical expressions. In SageMath, the definition is actually not that more complicated. But to run memoization, so we have to be mindful that there are 2 parameters. So what are there again? So n is the degree, so the first parameter is the degree of the polynomial. And the second parameter is the symbol of the variable in each polynomial. So therefore, we use a tuple nx as the key in the dictionary. So this is the first important modification for the memoization for polynomials. So keep that in mind. So there will be something else that will be important. So I will define x, the Chebyshev polynomial in x of degree n with memoization. So there is a dictionary. So this all looks like a regular Python function. So we will return the end Chebyshev polynomial in x, storing all polynomials in D. So here the dictionary is hidden, but one could return that dictionary as well if you would be interested in seeing the entire sequence. And actually we are interested, but what we are doing when we are asking here in the list comprehension, when we are asking for the Chebyshev polynomial, it is also a simple lookup what we will do. Alright, so this is the documentation string, always a good start. And then we have the first step. Be mindful here we have a tuple and an x. We check whether we have already computed the end Chebyshev polynomial in x. If that is the case, then there will be a dictionary entry, and we will return the value that corresponds to the tuple. So dictionaries are very flexible. So the keys, they can be composite data structures as well here. When we looked at the substitution command, we were actually also using expressions as the keys. Okay, so this is the dictionary lookup. Let me emphasize this with a tuple. And then I get to the three rules. So I remember them if you know to consult the rules. So the zeroed Chebyshev polynomial is 1. So now I'm doing everything at once, also the efficient memoization. So notice that I cannot return. So I must assign to the result variable. Then I have the second base case, which is the result is x. And then I have this general case. Then the result is 2 times x times t minus t. So I have the previous one. So recursion is powerful, but there's also a lot of things that can go wrong. And I almost made the mistake not adjusting the parameter that controls the recursion. So this is still, it's a 2-variable problem. So we have 2 arguments, but it's still a recursion that is controlled by one single parameter. So the n controls the degree of the polynomial controls the recursion. The other thing that I want to do is I want to expand. So that's the other issue that one has to be mindful of. So we spend an entire lecture on the normalization. So you see also here the Chebyshev polynomials are returned in their full expanded form, not in the format as they are listed here. So notice that expanded forms might lead to expressions well. So if I would not ask here Sage to expand, Sage would not expand and would therefore most likely also not execute the function calls. It might leave everything unevaluated, or it might evaluate this but then not really store the results as we want. So we would see an entire nested instruction. So that is something else that can go wrong here when we are dealing with expressions. Notice that we must normalize. Alright, before returning I must store, so using the tuple as the key, and then I can return the result. The function remains quite short. So I didn't make any type errors, I think. No, I didn't. So you see that the function is still very readable as it contains the three rules, the two base cases, degree 0, degree 1, and then the general degree. Let me verify whether this works. So I will compute the first 10 Chebyshev polynomials. And here you see you can verify the two base cases and also then the third polynomial. This all looks the same as before. And to make the point that this runs efficiently, I can time it. So let's suppose that we would be interested in the 100 Chebyshev polynomial. Then you see that this is computed almost instantaneously. Again, this works because the amount of storage required is linear in the degree. So memoization is so successful so we have a very the lookup will, even with 100, and 100 for current computers is a very small number, so even for 100 it will go immediately. 2 to the power 100 is a very, very large number. Just to make the case to end here, so the number of function calls that you would need would look extremely large. Even if every function call goes very efficiently, the number of calls will destroy, will not end. Okay, so I hope this lecture is interesting. Memoization is a very useful and very powerful technique. The main point being that we can follow the definitions, so there is no additional proof of correctness needed. And again, exploiting the efficient data structure dictionary from Python, which within Sage is directly available. There are the two extra steps that one needs to do, the lookup and the storing. Be mindful of the normalization of the expressions. Okay, I'm close to the 50-minute mark. Again, this is a very important lecture in this course. We are around the middle. I hope that this is both interesting and insightful. Look at the posted exercises in the lecture notes for this lecture that give you more practice with this technique.